Thank you everyone for joining me today. I'm Ron Bodkin, and I have been working with Hadoop for almost 10 years now. And a little bit about my background. I'm the founder and president of Think Big. I'll tell you more about Think Big later on, but the summary is we started the company a little over 6 years ago, always with the focus on helping enterprises get value from big data, Hadoop, and related technologies. And we've been working with a range of companies, whether it be in manufacturing, insurance, retail banking, media, advertising, healthcare, and beyond. And one thing that always struck me, right when we got started working at Think Big, helping enterprises use big data, was how much interest there was in Internet of Things data. That from very early on, we were working with companies like Network Appliance and helping them manage the data they were collecting from devices that were installed out in distributed locations around the world. So today I want to share with you some of my experience and our experience in managing data to get real value out of Internet of Things. So with that, I think we've all heard a lot of discussion around the various V's of big data: volume, variety, and velocity. But one of the biggest things, the thing that I think is the most important ultimately about big data is really the variety of the data. The fact that you have complex data sets with structure that's not so simple, often varying more frequently. It can be awkward to work with using more standard tools and techniques. So much of the data we think of in Internet of Things data fits that pattern. Sensors, audio, video, location data, images, logs, right? So that while size has some bearing, it's not what's most important. It's really the variety that makes is the hallmark of big data and why IoT data management is so important. If you look at it, some of the most important data sets that are unique to IoT are, of course, time series data. So things like sensors or reading or capacity data about devices, products, components, event streams. This is often thought of as logs, but logs really represent one way of capturing information about a stream of events. Those can be events that are external to a device that it observes or records, like acceleration, or they could be internal. IoT is very much about smart connected products that are on the internet. So the software activity of those products, alerts when they run into problem conditions, those are really important. And then there's relational classical structure and beyond, what we think of as more graphical, things like bill of materials and configuration and components and how things interrelate. So those are all important data sets when we think about the Internet of Things. Some of the use cases, there's so many use cases, but some of the ones that come up the most often when people look at Internet of Things are predictive maintenance. Can you use data about products that are deployed to do a better job of predicting failures and avoiding those by repairing, replacing, updating before there's a failure condition? Can you make it easier to do investigation and resolution of an issue on the fly? When something's going wrong, can you quickly search and look up and drill down and see detail about a complex system, a part in that system, and the symptoms that are creating issues? Can you, avoid the false positives and find of the storm of alerts that are so common in Internet of Things, which ones are critical? Can you do root cause analysis to see what's wrong? Even more proactively, can you do BI type scenarios of saying, well, what are anomalies or outliers or cases where Internet of Things data tells us something about parts of our system that are not working well, features that need more requirement for use, even just understanding frequency of use to say we ought to invest more in this part and understand what people are doing better because it's very popular, right? So connected products give us direct insight into how customers are using products instead of the traditional world of speculation around how things are being applied. So with that, let's talk a little about the changing technology landscape in data management. One of the big trends that Hadoop is right in the forefront of is the concept of a data lake. Collection of long-term data containers. One or more Hadoop clusters is a common way of implementing this, of course, that capture, refine, and explore any kind of raw data at scale. And can feed downstream facilities. And really the key here is, remember when I said that big data's hallmark is variety? Well, the reason why data lakes are interesting is because it's like there's a kind of Goldilocks governance, a kind of putting enough structure, enough organization into how you capture data that you're confident you have complete data and you maintain the data even as structures change over time, and you know something about how they were created without all the complexity of trying to parse and organize and fully curate the data, which is overwhelming given the increasing amount of varieties. So, we'll talk more about that in an example use case, but the concept of a data lake is high level part of the data management, but I want to unpack it and talk to you in a little more depth around what are some of the real patterns. As an architecture, we think about collecting IoT data sources through a variety of means. Streaming data, where you will have continuous flows, and message queues is a variant of that. But also there's still a lot of data that comes into data lakes that comes in for management that is handled through feeds. There's lots of work, of course, in preparing, making consumable data and being able to have enough governance to know things like the data is complete and secured, as well as doing some amount of organizing data for efficient access and downstream use from data products. So that's a high level around some of the architectural elements. Of course, we could do a talk on this all on itself. Another way of looking at it is when you think about a reference information architecture, there's a lot of phases that go in from data that's as it's acquired to being prepared and ultimately published. And not only is the relational data or traditional structured data involved in this, but so is the more complex data sets that flow in IoT, right? So you have data scientists that will work across all the layers, even with fairly raw data that's just been acquired and not structured. Data modelers that pick subsets of that data and prepare it and publish it out for broader access with more guarantees about it for the business to access, business analysts. And then, of course, IT needs to have a role in all of this. So this is a way of thinking a little bit about, again, high level, how does one manage the data? But we'll get a little bit deeper and talk about some specific patterns. So there's a lot of principles around how to manage data correctly in Hadoop. We see it's critical that since so often an IoT deployment requires you to have hundreds or even thousands of feeds for the different tables and the different sources, the different kinds of sensors that are producing data, you need to have good ability to secure data where it's sensitive, to be able to have metadata and lineage, to be efficient in how you store and utilize the data, and to have a real sense of being able to validate, clean, and profile the data so that all the users we talked about can understand and be confident in the data and make it easy to extend. A big part of having a data lake is being able to be agile and make it easy when analysts, when data scientists want to extend and make more sense of something in the data. They can do it on their own and it doesn't require an IT project to explore. So some of the changes are, as you've probably heard about, the concept of schema on read, right? And that is an important concept. But of course, data still has an underlying structure. So schema on read is often really more of a short form for saying you don't need to do all the modeling up front to reflect that structure. Instead, you could just expose as much as is helpful for your problem. And sometimes you can even do approximate things, like instead of getting parsing of something exact, you can write a quick regexp and get a 95% accurate analysis that gives you a flavor for the data without having to do all the work to write a perfect parser. Similarly, you've got this nice ability to have schemas that are more loosely coupled, right? That gives you more flexibility in your applications. So changes that happen upstream can be coped with downstream later on. But, the idea of data modeling isn't dead. That what you see is, as I showed in the reference information architecture, once you have data that's highly valuable and going to be used for a range of purposes, you do want to model it carefully and be accurate so that the broadest class of people can leverage it. And of course, we're also seeing some transference of ideas. Many of the good ideas of big data systems are being embraced by more traditional relational systems. Things like becoming more elastic and working with structures like JSON to make it easier to have complex structure in those environments as well. In terms of logical modeling, some of the big changes that certainly affect IoT are things like having JSON-like structures, ability to have nested structure with relations, arrays, and maps that reflect a lot more of the kind of complexities of real-world problems. Graphs, another one, having complex and dynamically changing relationships. Needless to say, this is a very natural structure to use for things like assemblies and deployments of composite items, whether it be assemblies in an automobile or whether it be in a manufacturing environment or a technology deployment of clusters of devices. And then finally, working with binary data, large object specialized data. So much IoT data is of this form that it's a complex format that's traditionally been, you had a specific specialized program that interprets and processes it. Being able to work with and have some first order representation for that rather than saying it's something that's somehow outside the system is a big change. Physically, there's a lot more options in Hadoop around how you actually lay data out on disk. And at the end of the day, when you write data on disk, you are making some modeling choices, right? How are you going to distribute the data? Things like key design or sharding, distribution, file formats. What computational algorithms are going to work against the data. And while it would be great if every compute engine worked equally well against every data format, we know that today that's not the case, right? So the other thing is when you've got all this complexity around how one can organize data, maintaining the integrity of the data is really an application concern. You don't have in a Hadoop system the concept of a foreign key like in a relational system. So if you want to maintain consistency between two views or two related concepts, it's up to your applications to do it. Because there tends to be a big shift, you have a lot of storage available, you tend to do a lot more denormalization and creating materialized views, duplicate copies of data to make access more efficient. Summarizing data can be orders of magnitude more powerful. Index lookups are increasingly costly. But basically, when you think about it, the amount of data that you can read sequentially is increasing with the density of disks, but the time to do a disk seek on a spinning disk is not getting much faster. So doing random access reads is increasingly costly in a big data system. So you try to avoid that. And finally, distributed systems, have more complexity, eventual consistency and reconciliation demands, right? So even within a single cluster, that's the case. And for BCP, for disaster recovery scenarios, we have multiple clusters. This is especially important. So with that, let's talk about some of the patterns for managing data that apply in the IoT space specifically. There's a lot of new patterns that we see in how one works with data in Hadoop. Denormalizing facts, profiles. We're really going to focus on the four highlighted ones: event history, timeline, assembly, distributed sources, and late data. Right? So these are all important patterns that we see often coming up in Internet of Things deployments that one wants to work with data. So event history is a very basic one. It's the idea to have a kind of fact table about common events that can allow things like analyzing consumer behavior across multiple devices in a context. That could be from a wearable device or telematics and combined with access from a mobile device, right? So it's a common scenario. We typically see this as being stored in a columnar format for efficiency reasons. So Parquet and OrcFile are two popular ones in Hadoop. Depends a little bit on the distribution you're using and the specific compute engines that you're using. The way this generally functions is you join the as was value of slowly changing dimensions to the raw data. So in our example, we might have an event, 1, 2, 3, and an actor ID, which might be the device, and a timestamp. But then we have not only columns about the event, but we'll have dimensions, things like, what information like, what was the configuration of the vehicle? What's the age? Who's the related account associated with that vehicle? And then another key element of event history is having the ability to have extension columns of data that are not parsed or modeled, right? So kind of a JSON-like data blob. That could be actual JSON. It could be stored in terms of H catalog description of a array of map of array items or otherwise. And typically event history is partitioned by event time buckets, like hours or days or 5-minute intervals, and can also be partitioned or bucketed in other dimensions as well, right? So if you wanted to, for example, do analysis on devices or vehicles, you might bucket it on the device ID of the vehicle. So if you were going to be doing analysis, you wanted to be able to do analysis on a certain specific vehicle, you could do it faster. If you had something else like accounts where a fleet of corporate customers, it might be very much more efficient to be able to bucket or subpartition on the owning account, so that if you were doing analysis, doing some data science work on events, you could limit your analysis to 1/20th of the data if you had 20 buckets or subpartitions where the specific customer whose data you were looking at was in only one of them, right? So this is a pretty foundational thing, but it has, again, the notions of denormalization, efficient storage of not only the basic event data, but the matching dimensional data. So it's not like a star schema, if you know data warehousing. And it also maintains the IDs, the foreign key values of the dimensions, as well as their translated values, which is very helpful when you think about if you want to go back and repair errors, for example, if there's ever a late arriving change to a dimensional value, for example. So that's a pretty foundational one, the concept of event history, and one that we see in a lot of deployments of Hadoop systems, definitely in the IoT space. Another one that's also real important is what we like to call timeline. If you think about the Facebook timeline as a place where you have a series of related activity around an actor, an individual, timeline is like that. Instead of giving you a set of events over time with actors scattered, instead it's somehow you have for a given actor, a given device, or a given component, all the events associated with it over time. So that could be the history of the device, that could be interactions of it, the actor or consumer, it could be a customer journey. It lets you really support analysis or do support lookups on specific items. Sometimes it can be a hierarchical, right? If you have a overall device and components and subcomponents, you may organize the actors with a hierarchical key, so you can scan over an entire cluster of items and look at their behavior, look at what's been going on with them. Right? And there's certainly some variety of approaches within that. How do you organize the data? You might have things like data about the actor as a whole, like what segments are they in? Are they active? Are they at risk for some condition? Have they just are they do they have certain characteristics like they're in the midst of an upgrade? You then will have typically a lot of different events, so you'll have an idea about the events, some timestamp, fact data about the events, and again, just as with event history, you can have other dimensions associated with the event, even extension data that's unique to the event to make it easy to extend the structure without having to create new columns for everything. This is, again, typically stored in a columnar format and can be partitioned. There's some variations in how one lays out timeline depending on whether you're looking for more of a near real-time system where updates can be done in milliseconds, or whether batch is sufficient where you're doing updates every hour, every few hours, every day, maybe every 15 minutes. And then another variant for timeline is it can hold cached algorithm values. If you have a machine learned model to say, what's the wear on this device and what's the risk of it malfunctioning, as an event comes in, you could look this up and immediately compare that to that model and potentially update it in real time as well. So timelines can be used to hold cached algorithm values. They can be stored in HBase for more near real time purposes, whereas if the focus is more kind of large-scale batch computation, they'll be often stored in HDFS and made available through HCatalog to engines like Hive or Spark SQL. Another pattern is the concept of event analytics. So that is being used for things like propensity or segmentation, right? So this is within the pattern, of timeline. Doing analytics on it, you can do things like in real time. You can do analytics on timelines, right? So what that means is if you want to look up and say, well, let me do an update to see if this thing's likely to be in a critical condition, it needs preventative maintenance, you can look at in real time all that happened, or you can have a batch model where you look at all event history and kind of take the next incremental set of events and update the model scores for all of the items that are in history, right? So typically this gets trained from timeline views, right? So you build the models by looking at per event data, or per device data, per component or assembly data, to see what are the characteristics of devices that have problems, for example, that fail, and build a machine learning model on those. Another example is attribution, right? Where you want to say, what's the impact of a past event on a new event? In IoT, this can be things like, how important is a given failure in predicting the likelihood of a device breaking, right? So this is natural to apply in a timeline view. And then for reporting and exploration, there's a couple of options. One is being able to, where the amount of event data in your timeline view is small enough and it's easy to use a SQL engine, you can simply use a SQL engine like a Presto or Impala on top of Hadoop. But where it's a large amount of data, using deep aggregates can be very efficient, which is a different pattern that we're not going to go into, but being able to pre-compute massive scale aggregates and then put them to something like HBase to make it easy to access them. We've built a technology called Dashboard Engine, but there's a number of approaches to doing that kind of deep aggregation. And then finally, discovery, being able to do indexing and lookup of events, which is a natural offshoot of when you've got a timeline, being able to use a search technology like Elasticsearch. You can put the key of the item and have pointers off to the timeline. This is especially powerful when you want to have many attributes you're indexing on. I mean, you just have a primary key. Timeline is typically easy to use, but if you want to be able to look up based on what component is in a larger assembly, it's helpful to be able to have that kind of indexing for discovery, as well as pure data science discovery, to be able to do things like Spark analysis on these events. So there's a lot of different kinds of analysis for IoT that these basic structures support. There's some of the key things in event data management. In some cases, merging identities is important, right? Discovering that a given mobile phone is connected with the owner of a personal fitness device. That requires some work in terms of how do you stitch together the identities or put them into an assembly. You have a part that gets pulled out of one device and put into another one. What happens there with identities, archival, exploration, of course, governance, right? So there's a lot that goes into managing these events. So we're not going so deep into each of the patterns as to work through each of those, but certainly there's a lot to getting these right. Another really important pattern is the concept of the network. Right. So when you think about having the ongoing status of the configuration, like parts of an assembly or related items and versions or software configurations within a deployment, which often it's not just physical devices in IoT and how they work together that is critical to understand, but it's also what are the versions of software and the interactions of software in those devices and within those devices that are important. Right. So graph databases are really compelling in terms of making it easy to have these at large scale, to do traversals and to do complex analytics on graphs like transitive closure. Things like what are all the parts and downstream assembled components that came from this batch of a production batch, right? So you can do analysis, traceability to see, if there was a problem in manufacturing a batch, what are all the devices affected, right, for impact analysis. There's some different technologies. In the graph world, there's a number of technologies like Spark GraphX that make it possible to do graph analysis on more general purpose storage formats like timeline and event history. But then there's also, technologies that are more specialized to do processing, both real time and in batch, very efficiently in a graph database. Neo4j is a very mature version of that that's open source, but Neo4j has a limitation that it doesn't support graphs that need to be in a cluster across multiple devices. It's not a Hadoop technology. Instead, it allows sharding, but only to scale reads. Whereas TitanDB is a graph technology that's built on top of HBase or Cassandra. So it can be run on Hadoop and can be accessed, and it scales, but it's less mature. So there's some different technologies, but network is an important pattern for IoT as well. And a common thing to think about in the IoT world is you're dealing with distributed sources of data. You don't have simple all or nothing feeds, right? So it's very common if you've got hundreds or thousands of devices that you're collecting data from, that you're going to have some that are offline, that, networks aren't available for a period of time, especially if they're mobile. So you need to know, do you have all the data or enough of the data? And to be able to have some confidence, when you're doing analysis, do you have enough data? And what do you do about incomplete data, right? So there's a lot that goes into that, control totals and heartbeats and watermarking, metadata, so that you understand lineage and you can make decisions about, do I want to reprocess data, right? So a lot of the complexity of ingesting IoT data comes from this. It's distributed sources of data, and it's really important to know if you have all the data and to build systems that when the unexpected happens and when you have delays and failure conditions, you handle it gracefully and you don't have a code red emergency that your system melts and nobody can understand what's going wrong, right? So a key part of that is the notion of late data, right? Data can be late because fundamentally IoT devices will go offline. They run out of power, the network's not working, they get disconnected, as well as due to failures in system infrastructure, things over the LAN, the WAN, servers being down. So metadata is important. You can do things around watermarking, so you have a sense of what's the typical distribution of delays, and at what point are you highly confident you're going to have 99.99% of the data. In an IoT scenario where you have devices that come offline, you're not going to be able to wait for all the data in most cases, right? I mean, if you have 1 in 10,000 devices that will emit data a week late, you typically don't want to wait a week to do analysis on your data, right? So you have to also think about, how do you handle it when you have truly late arriving data? What do you do with restatements? How would you reprocess them? Can you report on how much data is late? Typically there's some notion of bucketing on event time, and having a secondary bucketing on delay epoch, right? So if you sometimes will have eager reporting where you maybe do some incremental reporting on, hey, here's all the data we have now, but we know that enough data will arrive in the next 24 hours that we'll do a slight restatement between the first estimate of what's going on, what's our current state of health of the devices in the field, and then, okay, the next day we now have close the books on pretty good data where only a few outliers will come in late. So those are a few of the patterns that we see. Hopefully it gives a little bit more of a feel of some of the data management questions that come up in Hadoop with IoT. With that, let's just talk through a case study of putting this together. So in this case, as a customer that we've been working with for several years now, global manufacturer of storage devices that produce hundreds of millions of devices a year, each containing multiple complex components. And they're manufactured across locations around mostly Asia. Some components are not manufactured in-house, but come from suppliers. And there's up to 1 gigabyte of data generated during the life cycle of testing, manufacturing, testing, deployment in the field, ultimate analysis as problems occur, phone home data around those devices. So some of the challenges that were there when we started working on this problem were there's a lot of time wasted playing Where's Waldo with the data, trying to track down for engineers, what's going on with this failure? Can I get to the data set or the test that happened when this thing fails in the field and understand? This could be pretty significant, right? When you have a customer that says, if you can't explain to me why this particular device failed, I'm going to return a multi-million-dollar lot of items and assume they're all bad. That puts a lot of pressure on engineers to track down root cause of why did the one fail, right? Speeding time to market. So the faster you can figure out what things aren't working in developing the product, the faster you can ship at scale. And in a high-tech manufacturing arena, the ability to ship a product a month early is incredibly important for gaining market share and for amortizing the investment in building that product, where product lifespans are typically measured in quarters and not years or certainly decades. And customers, of course, are demanding faster failure analysis, wanting to understand if things aren't working, why, and in fact, where possible, being proactive in avoiding things failing in the first place. So technically, challenges around this were, having silos, lots of data in different manufacturing facilities that weren't put together, the difficulty storing and exposing the binary and other data types that were being used in different stages, not having a platform for doing the analytics. So many organizations find themselves this way with IoT data, where they have the ability now to collect it and transmit it, but they don't have anywhere to store it, and they don't have anywhere to analyze it, right? They don't have the data volumes. The data volumes are exceeding the traditional data warehouse. And the first version was often only do a small amount of data that we believe will be critical and keep it for a limited amount of time, and then put things out to tape where it doesn't ever really get used except in the most dire circumstances. So one of the key things that we've been able to do is expose the entire DNA of these devices, from development to manufacturing and reliability testing, all the way through to behavior in the field to increase the operational efficiency and quality of these devices. In order to do that, we used a Hadoop deployment, Cloudera distribution on Amazon Web Services, and fed in data from a variety of sources: shop floor data from multiple sites, assembly data, configuration data, data from suppliers, shipment data, returns data, downstream testing data on devices in the field, into a platform where, again, as we saw, the data is stored in a raw form in a data lake, and then it's refined so that end-to-end integrated views of the entire timeline of the device are available to make it much easier to do analysis. And then this is fed into a variety of downstream analytic platforms. Ad hoc analysis for failure analysis to say when something breaks, make it easy to pull the right data to do the investigation. Batch screens so that models are built and continually improved to say when things fail, why do they fail? End-to-end traceability applications, and downstream, summaries being fed into the data warehouse as the data gets refined to answer a variety of ad hoc questions. So this is the overall deployment that we have created working with the customer. And one of the key use cases was the binary data, right? So that there's lots of challenges around decoding this data. The data needs to be kept for 5 years for warranty reasons. There's petabytes of binary data that's therefore needs to be retained and made online. And it's a classic example of the need for schema on read. The development and process engineering teams here will frequently change the manufacturing and test data. So, and they don't typically think about making sure that when they're making a change, as they're rushing and trying to improve something in engineering, how do they make sure that downstream and future analysis will work well? So the decoding will change, and it typically can't be done. It won't work to break the system if something isn't in the right format you expected. So it's very hard on traditional DBMS, where you would be finding errors and needing to continuously purge data and retry and rerun rather than being able to parse data on the fly after storing it in a raw format. And that's a big advantage here of the ability to parse. And the other thing that's notable was with 5 years of legacy data in Hadoop, we were able to use streaming to take in existing code, such as in C++ and Python, that will parse data, so be able to integrate existing parsers into the system untouched, with an adapter framework. Another important use case was wide structures. There can be tens of thousands of parameters that are collected over a few months for a single device. So having that kind of denormalized structure, which you'll recognize as an instance of the timeline pattern, right? Having that wide structure with all the data about a given device, making it much easier for end user analysis. And then the third is really the ability to have massive compute to do a parallel analysis, right? So, doing investigation of a particular issue, you can see plots of devices where the engineering team scanned hundreds of billions of test points across about 10 million devices. And then the outliers could be plotted, which allowed in drilling down on what was wrong. This is the kind of thing that would be incredibly hard to do in a traditional system where you could painstakingly investigate and look at one device at a time. You couldn't harness the power of a massive compute cluster to do analysis. And the last thing that we've been excited by is having this data in Hadoop has allowed us to do hackathons with a customer, where people from various different teams in the company are able to participate and prototype their ideas against raw data. And then the ideas that are working well can then be made more efficient. So back to this idea of agile modeling. Hey, here's some data that we want to expose in a more standard form. It's worth it. There's value here. We'll parse it out. We'll take it out of the extension columns and put them in as a parsed first order column, or maybe even a separate materialized view for efficient use in a downstream application. So, a couple of conclusions. One is there's some value in using probabilistic data structures to optimize, right? So that's a modeling technique we didn't talk about, but comes up often, at massive scale, especially if you want to do things like count unique devices that might that are experiencing some condition, or have things like filters to say, do I even need to look at this partition at all, or can I, basically index it and avoid, looking at it if I'm doing analysis on rare events. And also, there's a lot of anti-patterns. So what do you not want to do when you're working with data, IoT data in Hadoop? Well, you don't want to treat Hadoop like a giant database, right? You don't want to put your data in third normal form with lots of joins required for all analysis, or even, more traditional data mart forms like star schemas and snowflake schemas that, again, still require a lot of joining. And there's some cases where, if the dimensional tables are small enough that this can be held in memory. But again, index lookups are slow. Partitioned reads of denormalized data work a lot better. So, the classic relational approach does not work well. Over time, I think we're going to see more of a hybrid where you'll see more of these techniques being supported, whether with solid state drives, which still tend to be cost prohibitive in Hadoop environments, especially at large scale, better optimizers, updates to the platform. There's a lot of desire to make these work better. One thing a lot of people say that I don't believe is, well, look, won't we just be able to cache all this data in memory? And if you look at the growth of data, even just from cell phones, the pace that device data, such as from cell phones, is increasing is far faster than the density of memory. In other words, working with IoT data is not going to be it's not a good bet to say, oh, we'll just use in-memory techniques. You're going to have ways of storing it on disk and being able to comb through that disk efficiently. And that's why fundamentally traditional data warehouse patterns, laying out data, is an anti-pattern in the Hadoop world. Again, before we get to questions, quick summary of us at Think Big. As I told you, we are a big data services company. We help customers through the life cycle of working with big data, putting together architectures and roadmaps, building data lakes with not just great consulting, but we've built a lot of frameworks that codify the patterns that we've seen over and over again to speed time to delivery, doing analytics and data science. I didn't talk a lot about the analytics, but in the IoT world, so often the analytics on the data is initially just being able to get your arms around what's going on. Being able to look up a device, being able to do a quick search, being able to run reports over this dark data, the behavioral data of devices as deployed, but then moving on to data science, building predictive models, identifying outliers, anomalies, dealing with things like predictive failure is incredibly powerful, and we help customers with that, as well as managed services, training, and support. So, we work with a lot of technologies. Obviously, we do a lot with Hadoop. Spark is incredibly important. Kafka for HBase is very important in a lot of the real-time use cases within the Hadoop environment. And we see Presto, as well as Impala and others, as often being really valuable query engines on top of the big data stack. So that's a little bit about us and what we do. And then finally, I'll just conclude with, so much of IoT is about blending data together, and having the right ways of the patterns and practices for managing data is foundational that lead to effective analytics. And with that, we've got just about 15 minutes left here, and I will turn it over to you for questions. So I see so far there was a question, can we have access to the slide deck? And absolutely, I would be happy if you want to get a copy of the slides, you can send me an email here at this email address, ron.bodkin@thinkbiganalytics.com. You just send me an email and say, can I please get a copy of the slides? I'll point you to a location to download them. All right, that was one question. Any other questions? So the question of, the presentation is awesome. Could you also give an example on how retail banking leveraged Hadoop in practice, like fraud detection, digital media, credit rating? Good question. There's a lot of things we see people doing in retail banking. Some of the common ones are around understanding consumer behavior. So being able to look at things like, how do I put together data about what a consumer is doing on mobile, what they're doing on web, what they're doing in the branch, what they're doing in the call center, to do things like better understand what their interests are, what kind of upsell, cross-sell opportunities you can present to them, personalization, as well as churn, right? Finding places where customers are at risk of leaving or taking some of their business away, to be able to respond to them more effectively. That's common. Fraud and money laundering and security are also important use cases in the retail banking sector. Right? So those are all ones that we often see. So that was the one question. There's plenty of other use cases. There's just a few that jump to mind that we've worked on. The question is, why would someone choose Amazon services such as Amazon S3 over Hadoop and Amazon Kinesis over Kafka? And, that's a complex question, right? Like a lot of architectural questions, there's trade-offs. When we see people running on Amazon, we often actually help customers run Hadoop on Amazon, right? And when they do, we are seeing a lot more customers use the commercial distributions, Cloudera and Hortonworks, rather than Amazon Elastic MapReduce, because when you have a long-lived cluster, there's a lot more services in the commercial distributions, integration of things like Spark. Although there's still a real question that the center of gravity of many Amazon deployments is Amazon S3. And so HDFS becomes more of a caching layer for data that's going to sit in there for a medium term, but the long-term place where data gets synced and stored is S3. So it is a big difference between using a data lake where HDFS is fundamentally the long-term storage, and in Amazon, where it's more typically S3. Now, Kinesis versus Kafka is an interesting one. We've seen a lot more deployments of Kafka just because Kinesis is really compelling if everything you're doing is on Amazon. It's really easy to stream data from servers that are doing your event serving, your IoT device data on Amazon, and connect it kind of seamlessly through Amazon's infrastructure over Kinesis to downstream analytics applications. On the other hand, if you've got needs to feed in data from non-Amazon environments, Kafka has a lot more integration. There's a lot more ways of collecting data in Kafka and working with it. And of course, it's much more portable, right? And that's another thing that's a big difference is a lot of Amazon services are proprietary and work only on Amazon, whereas when you go with more open standards like Apache Hadoop, Apache Kafka, it's more portable and works in different environments. At the same time, credit to Amazon, they make a lot of their services work really well and compelling, and they integrate together very nicely. So, you see companies saying, well, look, we may not want to be on Amazon forever, but if we build something quickly and it works well on Amazon, we're willing to have that trade-off, and we may have to rewrite some things if we want to move off. And the next question I got is, can I speak a bit about the disaster recovery and security of the big data sets? And that's a good question. So there's a couple of elements. In terms of disaster recovery, the way that we will typically help customers, there's kind of two philosophies for how you have disaster recovery. The typical one is to say, well, look, I want to, in order to have ensure the data doesn't get lost, I want to have another cluster, another online system where my Hadoop data is being backed up, right? So it's basically the most common approach is to have more than one Hadoop cluster and more than one data center that's in production, or one of them will be a standby. So you can either have active, they're both active, or active standby, where you have a disaster recovery cluster that has all the same data. You can do that either by ingesting the data into both clusters simultaneously and doing the processing, or simply replicating, copying data on intervals from the primary cluster into the backup or standby cluster. Sometimes companies will have a standby cluster made available for other purposes like ad hoc analysis, data science. Depends a bit on your service level agreement and whether you want true business continuity, where there's very short windows where something can go down versus the ability to recover it all. The other approach that people will use for disaster recovery is some form of more cold storage of data. That could mean backing your data up to Amazon S3 and only spinning up a backup cluster that's needed to process the data when it's in S3, rather than having a standby cluster that's idle or being used for another purpose. Or, in other cases, we do see companies saying, well, maybe we will have some kind of a filer or even a tape-based backup. But, filers and tape-based backups tend to be a little bit tricky to make work well at Hadoop scale. In terms of security, that's also an important consideration, right? So the security in Hadoop is definitely something where you want to have defense in depth. You want to have, the classic deployment of Hadoop in the early days was that Hadoop was a trusted environment, and you limited access to a few people to working within the environment. You had gateways to access the data in that were secure, right? So you could run a Hive query, for example, a SQL query, or submit jobs through a gateway that checked your permissions and nobody else got on the inside. Today, we don't see a lot of companies deploying it that way. We see them instead having defense in depth, where they will use Kerberos. So you have strong authentication so that even if someone gets into inside a cluster or running on an edge node, running arbitrary code, they can't do more than they have permissions for. And we're seeing, rapid improvement in services like Clutter's record services approach, or Hortonworks Ranger, that provide more fine-grained security primitives for access to data. It is a bit trickier in the Hadoop world because you have this flexibility of so many different engines that can access data that it's not enough, for example, to say, well, I've secured how Hive reads data in Hadoop. What if somebody downloads and installs Apache Flink, right? And now they're using a whole new streaming engine on your cluster. Do you have it secured then? Right? So security has to take that into consideration, that the data itself needs to be secured either through a gateway or through things like encryption and key management that don't allow you to access data if you're not entitled. So that's a little bit about security. Of course, it's worth a whole webinar on its own, security in Hadoop, so that's high level. Next question was thoughts about schema evolution. And I think, the key part of the patterns I talked about in data management are you do have schemas evolving rapidly, right? So the ability to record data in a raw form, to have enough metadata to know something like what version did it come from, so that it's easy to know. You can associate with the schema, or as you discover later on a schema change, you can understand that. There's certainly, when you have parts of the model that you do need to parse out and rely on, when the schema changes, there will be cases where you have to recompute, reparse data if you didn't get that schema change right. So, so there's an art. A lot of the value of these patterns is it facilitates schema evolution, and the agile approach to working with data for IoT means you don't you're not as vulnerable, because only the critical data sets that, fields and values that change, that you're truly dependent on, are going to drive more work when they change instead of everything. And then there was a follow-on, why is it not easy to maintain schema evolution? Well, it just depends on the patterns you use, right? The challenge around schema evolution is if you have a system that depends on exact schemas in a given form, often upstream things change and it breaks applications. It creates, complexity of reprocessing, or even worse, silent errors, things that are incorrect and not caught, right? Next question is, which of the design patterns will work for smart metering applications if the goal is to build a kind of recommender system for the customer, right? And so for that, I would say, the smart metering applications, again, what you're seeing is a whole stream of events associated with a customer. So your recommender system is going to have two parts to it. It's going to have a part where you have the history around the metering, but you're also going to want to associate the meter events with data about the customer, right? So what's their account? What's their history of payment? So you kind of know what their historical bill and usage is at a high level. So you can train a model to do recommendations offline on all that data. And then, as events come into the metering, it can then be scored. So if you start to see changes in the behavior, you can say, this is a good example. You might have a need for something like sessionization, where it's not a single meter event, but it's the pattern over the last, say, 10 minutes to say, hey, this is ramping up in this way. It's got this signature. It's likely to mean the following event is happening. And we have a recommendation for how, if you're doing the following thing, it's inefficient. Here's a way that you could, for example, save energy, right? So you technically would have, timeline, which would be for the given customer, what's this time series of metering events, as well as event history that's used for training models and scoring them offline. And you could do real-time updates to the models and timeline to make the recommendations. The question is, what tools do you use for testing, pipeline, or monitoring? So we actually have built some of our own frameworks and are working with a variety of different tools, enterprise schedulers, Apache NiFi, and beyond, that make it easier to put together pipelines that capture the metadata at each stage and monitor them, right? So to be able to see on the one side, at a higher level than a job, but for a feed or a regular process, what's its health? Is it working? And even at the other side, for a data steward to say, is the data up to date? Are we meeting our service level agreement, or is it stale? And we need to maybe investigate, well, why? It turns out that there is a fundamental fatal error. The processing code can't process this changed format, and that's resulted in a delay, right? So we have something we call pipeline controller that does that we built because there's pieces in open source, but putting it together is something that we've found to be incredibly valuable. So and I think we all see there is a session on security at 3, so it was a good leading question. My 1 to 2 minutes on security was not really enough to cover security in Hadoop, so you can hear a whole hour on it coming up in about an hour. Which layer in the data pipeline should do validation? I think, ultimately, validation is important at a number of layers, right? Right at the point of ingestion, you want to be able to do some amount of profiling and detection of invalid data. Now, typically the pattern in the big data system is you will segment out invalid data, put it in a separate location. It can still be accessed as raw data, but at least it's somehow tagged and known to be invalid, right? But then downstream, as you're doing downstream processing, you often will have more advanced validation. So for example, detecting internet traffic that's coming from a robot. That's not typically done right at ingestion, but instead, that's a smarter machine learned algorithm to say, what's the likelihood that this activity is in fact a bot and not a human, right? Related to that, should message transport do validation, or should the end consumer do validation? I'd say that in most cases, I'm a fan of having more the end consumer, or more in the cluster environment. You do the validation, you kind of capture the data with the minimum amount of changes and modifications in a raw form, because there's always the risk of software bugs. And if you try to validate data, transform it in the transport layer, you're exposing yourself to the risk that if there are bugs, you can't ever recover that data. Now, that's not always feasible. There's some IoT applications where you have massive amounts of data and you just can't afford to move it over a small network connection. You have to do some validation and even fanning down. So it's not like this can always be done. Next question, how does one get started on understanding or getting trained on the Internet of Things ecosystem, or start learning on a small scale to help with a project maybe? And I think I would say when our teams, when people join our company, we do put them on initial projects where we work with some Internet of Things data and they're able to get some experience. There's some public data sets out there. And, I don't know off the top of my head. I mean, there's things like more often the first data sets that we're using are things like Twitter data or stock data. We do have some public data from airplanes and the FAA. So doing a small project, as well as, there's obviously a lot of online courses as well. And then we got like 1 minute left. And I will send the slides. So if you would like, send me, let's see, I'll figure out how to share the slides. I'll get them to Francis. But if you want the slides, also feel free to send a note. And again, feel free to reach out to me if you want the slides or you want to be in touch. Tweets are welcome. I hope you enjoyed the talk today, and thank you for giving me an hour of your time. I enjoyed getting a chance to share with you and the great questions you asked today.